Good morning or good afternoon or good evening. My name is Yuta Hayashi, and I belong to Meteorological Satellite Center of Japan Meteorological Agency. I am working on the volcanic ash products derived from the observation data of JMA's new geostationary meteorological satellite, Himawari-8. It is a great pleasure for us to have a chance to talk about our Himawari-8 in this preparing for the next generation of satellites sessions of virtual laboratory. In this session 7, I'll introduce Level 2 products and RGB composite imageries derived from Himawari-8 data. Okay, let's begin. Okay, this is the outline of the session. As an introduction, I'd like to overview the features of Himawari-8. Next, I'll introduce Level 2 products of Himawari-8, beginning with explaining the definition of Level 2. Here, some examples of Himawari-8 products, such as cloud products, atmospheric motion vectors, and clear sky radiances, are briefly shown. Finally, I introduce RGB composite imageries. Here I'll explain what RGB in the first place. Then, the usefulness of RGB and how to adjust the visual aspect of the imageries are shown. After that, I'll show some examples of RGB composite imageries. Okay, here I'll begin with the Himawari-8 overview. This picture shows space-based component of the global observing system. Each country has been launching its own satellites, and those satellites cover all over the world. There are mainly two orbits for meteorological satellites: geostationary orbit and polar orbit. The altitude of geostationary orbit is about 36,000 kilometers. On this orbit, satellites round at the same speed of Earth's rotation, so we can always see them at the same position stationary. On the other hand, the altitude of the polar orbit satellites is from 800 kilometers to 1,000 kilometers. They fly at lower altitude orbit and always pass by both poles. JMA's new geostationary satellite, Himawari-8, here stays about 140.7 degrees east longitude. Okay, this map shows the coverage of Himawari-8 observation and countries included in the area. Is your country included? About 30 countries or regions of NMHS, the technical and hydrological services, use Himalaya data for weather forecasts, and total number of people is approximately 2.2 billion. Besides these, we also provide Himalaya data to NOAA, UMETSAT, and domestic research institutes. The remarkable feature of Himalaya 8 is the improved resolutions of the advanced Himalaya imager, called AHI. There are three elements. First one is spatial resolution. Compared to our previous satellite, MTSat series, the spatial resolutions are almost doubled. Second one is temporal resolution, which means observation frequency. For full disk observations, it took 60 minutes by MTSat, but it takes only 10 minutes by Himalaya 8. For regional observation around Japan, Himalaya 8 can observe every 2.5 minutes. Third one is spectral resolution. Himalaya 8 has 3 visible bands, 3 near-infrared bands, and 10 infrared bands. Total 16 bands are more than 3 times in number than those of MTSat. Thanks to the 3 visible bands, we can obtain full color images like this. The improvement of resolution is often compared to the evolution of television. Data amount of Himalaya 8 observation is approximately 50 times larger than those of MTSat. This big leap is like the evolution from black and white TV to the high-definition TV. With higher spatial, temporal, and spectral resolutions, it is more likely to detect certain substances or phenomena, such as CB clouds, volcanic ash, SO2, and ozone. That we can retrieve geophysical quantities like cloud top height more precisely. With these advantages, we can enhance Level 2 products and improve RGB composite imageries of Himalaya 8. Okay, let's go on to the next topic. Here, I'll introduce Level 2 products of Himalaya 8. First of all, what are Level 2 products? Products derived from satellite observation data are categorized by the processing levels they undergo. Definitions of processing level slightly vary by centers, but generally interpreted as follows. Level 0 means raw data. Level 1 means converted instrumental data, such as brightness temperature or reflectance. Level 1 often subdivided into 1A, 1B, 1C, and so on, according to the conversion steps. Level 2, focused here, means geophysical quantity products retrieved from single instrument data at the same resolution and locations at the level 1 source data. Level 3 means products mapped on a certain grid, usually uniform space-time grid scales. Level 4 means products compose multi-sensor and/or multi-satellite products. These level definitions are summarized in each organization's website here. And so please refer them if interested. Okay, here I enumerate level 2 products of Himawari 8. Cloud mask, cloud type, cloud phase, and cloud top height. Atmospheric motion abbreviated as AMV. Clear sky radiance abbreviated as CSR. And rapidly developed cumulus layer and aerosol or agent. These 5 products are now operationally produced. But more, there are products under development. Volcanic ash, sea surface temperature, optimal cloud analysis, atmospheric stability index, and solar radiation. I'd like to explain these underlying products in the following. First, I show cloud products. These consist of cloud mask, cloud type, cloud phase, and cloud top height. The algorithms used to retrieve the information are based on NWCSAF. This is a nowcasting satellite application facilities and NOR-NESDIS products. These products become inputs of other level 2 or level 3 products, such as high-resolution cloud analysis information explained later, and clear sky radiance, and so on. We evaluate and validate our cloud products by comparing with Accor Modis cloud products. This shows cloud mask comparison of AHI with Modis. Here, red and light blue, right? Red and light blue areas denote discrepancies between two products. Assuming Modi's product as 85% accuracy. In the same way, it is found that cloud phase has about 90% true positive rate, and the bias of cloud top height is less than 1 kilometer. Here I show the high-resolution cloud analysis information, abbreviated as HCAI. This consists of cloud products, snow dash detection, and image quality information. The difference between these and previous cloud products is that these HCAI are products on latitude-longitude grid in 0.02 degrees. Data coverage is from 60.01 degrees south to 60.01 degrees north latitude, from 79.99 degrees east to 159.99 degrees west longitude. These products are produced hourly and are used for operational forecast and monitoring. JMA provides these products to some national meteorological and hydrological services with the resolution appropriately modulated. Next, I show the atmospheric motion vector, AMV. AMV was also in operation for previous MTSAT product. This product is usually used for numerical weather prediction. Left and right panel shows Himawari 8 and MTSAT 2 AMVs, respectively. You can clearly see great increase in number of retrieved AMVs from Himawari 8 data. Since the observation frequency is improved to every 10 minutes, the rate of successful AMV calculation or tracking by pattern matching method is largely enhanced. This shows so-called OB statistics of Himawari 8 and MTSAT 2 AMVs. Here, O means retrieved AMVs. We wrote here OB speed. And B means NWP first guess. I wrote here BG speed. We use JMA global model as NWP, numerical weather prediction data. This statistics shows how much the AMV is consistent with forecasted wind data. As you can see, AMVs from Himawari 8 have much better correlation than those of MTSAT 2. Next is Clear Sky Regions, CSR. This product shows area averaged clear sky brightness temperature. This product is usually used for numerical weather prediction. Full disk products are produced hourly for all IR bands and distributed via GTS mainly for NWP communities. Spatial resolution is 16 lines by 16 pixels, which means about 32 kilometers by 32 kilometers at sub-satellite point. This is an aerosol product. This product consists of aerosol optical depth and angstrom exponent. The latter is related to the particle radius and can be derived only over the ocean. Retrieval algorithm is called lookup table method, abbreviated as LUT. This table is optimized for agent dust, so this algorithm cannot be applied to the other types of aerosol. This product is for internal use of agent dust monitoring, and data assimilation system of this product is now under development in collaboration with JAXA, Japan Aerospace Exploration Agency. Since the algorithm shown above uses visible band observation, the product cannot be retrieved during nighttime. Instead, we are planning to apply volcanic ash retrieval algorithm, explained later, to detect aerosol during nighttime. Finally, I show volcanic ash product, which is now under development. We are to adopt retrieval algorithm called Volcat, developed by Noah Disness. Implementation of Volcat at Meteorological Satellite Center of JMA is underway. Expected products consist of ash top height, mass loading, and optical depth. These volcanic ash information are crucial for aviation safety and will be used by VAAC's volcanic ash advisory centers in order to issue precise advisories to aircraft. The preliminary volcanic ash products of imagery 8 are planned to be experimentally provided to JMA's Tokyo VAAC for evaluation and validation. This figure shows preliminary results of Volcat for the eruption of Laun volcano in Indonesia on 13th July 2015. Now, introduction of level 2 product is over. Shall we go on to the next topic of RGB composite imageries? First, I'll explain RGB techniques from the basics. Okay, What's RGB? R means red, G means green, and B means blue. These are the three primary colors of light, and they constitute color space expressing additive color composite. This figure shows the three primary colors of light, red, green, and blue, and their additive colors. The LGB composite imagery is a technique to display a color using this property of the three primary colors of light. In other words, you can depict all the colors by adding these three primary colors at an appropriate proportion. Then, why we use LGB techniques for satellite images? Here shows Himawari 8 full disk observation data at 00 UTC 16th November. As you know, there are 16 bands. Forecasters should monitor all of these data and also differences between one band data and the other. Moreover, these data are produced every 10 minutes. Can you handle them? There are too many bands to monitor. Here appears the LGB technique. What we should do is just allocate the three primary colors of red, green, and blue for multiple bands of satellite images, and then compose them. Thus, information of multiple bands are incorporated to one image. Since various information are derivable by one LGB composite imagery, it is very useful for monitoring by forecasters. The European Organization for the Exploitation of Meteorological Satellites, EUMETSAT, has been developing the composites. It means they explore how to compose satellite images to make an LGB composite imagery useful for monitoring. These are LGB imageries for MSG Severi satellite, developed by EUMETSAT. Each LGB natural color, day microphysics, night microphysics, day snow fog, day convective storm, dust, and air mass. I'll explain how to monitor the LGB with some examples later. You can get these LGB imageries in near real time on this website. I load it here. These are the same LGBs for Himawari 8. Our near real-time monitoring website is here. Okay, now let's quiz. Here are 16 bands, not bands. There are 16 bands. Find hot, juicy pork buns. Of course, you cannot find them only from this information. Now you can use these special glasses. This is a hot vision glasses, and you can find hot buns through these glasses. This is a juicy vision glasses, and this is a pork vision glasses. Using these three pair of glasses, you can find hot, juicy pork buns. Have you already found them? I think it's possible, but a little troublesome. Now use colors. Let's color each pair of glasses in red, green, and blue. Then compose them. Maybe you can put these three pair of glasses at once. Then the set of buns seem like this. According to the LGV technique, hot, juicy pork buns appear white, as denoted here. So this one is the hot, juicy pork bun. By using RGB composite image, you can find hot, juicy pork buns at a glance. Okay, let's get back to the saturated imagery. The red panel is the visible band imagery, and the light panel is infrared 11 micrometers imagery. Visible band imagery corresponds to the thick cloud vision glasses, and infrared imagery corresponds to high cloud vision glasses. Using these glasses, please find thick and high clouds. It means CB clouds. Allocate red and green to the thick cloud glasses, and blue to the high cloud glasses. Then compose. In the same way as before, thick and high cloud areas appear white and easy to recognize. If you want to focus on the low-level clouds, just look at the yellow area. You can understand the reason by considering with this color chart. Yellow denotes thick but not high clouds. From here, I'll show how to adjust visual aspects of imageries. For extracting and enhancing specific phenomenon, such as thick and high clouds, adjusting visual aspects of RGB composite imagery is important. The visual aspects of RGB composite imagery can be manipulated by adjusting gradation range or grayscale range and gamma collection. Here I load RGB composite imagery, but this is also true with the single band satellite imagery or difference imagery. In the following, I'll explain how to adjust the two parameters with showing examples. First, adjustment of gradation. Here is an infrared imagery. Sorry, this is not memory aid imagery, but one borrowed from UMSSAT training materials. The gradation range of the left imagery is from 180 Kelvin to 340 Kelvin, whereas that of the right imagery is from 180 Kelvin to 233 Kelvin. You can see some clouds very clearly in the right imagery. These clouds are supposed to be thick and high CB clouds, since they have low brightness temperature. Thus, you can emphasize CB clouds by adjusting gradation range of the infrared imagery. Here is another example of adjusting gradation range. This is an imagery of difference between two infrared bands, and often called brightness temperature difference. It is known that you can detect dust, for example, sandstone, yellow sand, or volcanic ash, from the brightness temperature difference between 12 micrometers and 10.8 micrometers infrared bands. Comparing the two images, you can find that dust areas are emphasized by changing gradation range of brightness temperature difference imagery. Next, I'll explain gamma collection. Gamma collection is a method to emphasize the change rate of the gradation of the imageries. This graph shows the mapping function of gamma collection. Horizontal axis is the gradation values before mapping, and vertical axis is those after mapping. You can see that the mapping function is a power law, and the gamma value is its exponent. By adjusting gamma value, you can vary the change rate of gradation. This is an example of gamma collection adjustment. These are all visible band image. The middle panel is the normal gradation with gamma value of 1. In the left panel, gamma value is set to 0.5. And the right panel, it is set to 2. You can see the change of looking of the land surface. That's I can't see by adjusting gamma value. We have made these LTBs based on the UMS method, but the parameters are slightly changed. This is the table of Himawari 8AHI specifications. There are 16 bands, and wavelengths meaning is denoted here. And here shows the using bands for RGB imageries. Natural color RGB uses bands 3, 4, and 5. Day microphysics uses band 4, 7, and 13, and so on. In the following, I'll show the example of natural color RGB and dust and air mass. Okay, natural color RGB. This is for detection of snow, ice, and vegetation and clouds. This is the specification of natural color RGB. Red is the band 5. Green corresponds to band 4. And blue is band 3. All the gamma value is set to 1. And compose them will obtain this natural color RGB imageries. Here shows the interpretation of colors in the natural color RGB. This color means ocean, and green means vegetation. Brown means desert, and light blue means snow. These 4 is the land surface properties. And here, this color shows low-level water clouds. And this color shows high-level ice clouds. Here is the example of natural color RGB. You can see from this image, vegetation appears in green, desert or bare ground appears in brown. And this area is covered by snow or ice. Next is dust RGB. This is for detection of yellow sand or Asian dust. First, I'll explain the algorithm of dust detection. By seeing the difference of the brightness temperature of band 15 and 13, you can distinguish yellow sand, dust, or volcanic ash formed meteorological clouds. This image shows the Himalayan 8 brightness temperature difference image. And here is the yellow sand. And this is the example of dust RGB. We should here red correspond to the difference between band 15 and band 13. Green corresponds to the difference between band 13 to band 11. And blue is band 13. The pinkish area we found here corresponds to the yellow sand. This is the brightness temperature image showed before, but it's easier to detect the yellow sand area on this RGB. Okay, this is the interpretation of colors of the dust RGB. The pinkish area corresponds to the dust and the yellow sand. And the colors of meaning is denoted here. Okay, next is the air mass RGB. This is for analysis of air mass and jet stream. This is the specification of air mass RGB. Red corresponds to the difference between band 8 from band 10. Green is the difference between band 12 and band 13. Blue is the band 8 data. And when we compose them, we obtain this air mass RGB imagery. This is the interpretation of colors of air mass RGB. This reddish brown means jet, and purple means cold air mass. Green area means warm air mass of high humidity. And this color means warm air mass with low humidity. This is an example of air mass RGB. You can see from this weather map, here is the cold low. And this color means jet stream. And in the south, greenish area means the warm air layer on the north. Okay, lastly, I'll introduce our website of RGB training materials. Here is the Meteorological Satellite Center website and Virtual Laboratory web page. Here we added link button to the RGB training page. if you click that button, we jump this page, and here outline of RGB composite imagery based on the human set technique documents. And here are materials or WMO recommended schemes. Almost all imagery are derived from Himari 8. And introduction of these RGB can be obtained from here. And here, materials except for WMO recommended schemes. You may know the JMA True Color RGB, and its instructions can be obtained from here. Okay, let's summarize. Advantage of Himari 8 AHI: improved spatial, temporal, and spectral resolution, brings enhancement of level 2 products and RGB composite imagery. And I introduce Himari 8 level 2 product by making the most of Himari 8 abilities, resolution and or precision of existing level 2 products are very enhanced. And some new products, like volcanic ash products, are under development. Lastly, we introduced RGB composite imageries. And by utilizing abundant observation bands of Himari 8, several RGB composite imageries specialized in certain phenomena are produced. Okay, thank you very much for your kind attention.